Okay, part 3 here. So, part 3, number 13 here, we're looking at systems of equations. So we have 2x plus y equals 5 and 3x minus 2y equals 4. Now you're asked to solve this by substitution. On your exam, I don't really expect to force you into a particular technique, but you do need to know both techniques. They are both really handy for different things, so make sure you're robust with your techniques. But this one does end up being a nice application for substitution because you have this nice y there that's clean in terms of having a nice 1 as a coefficient. So you're not going to have any too terrible fractions dealing with this. If this had a 7 in front of it and we had to divide by that 7, it would have been uglier to solve for. Here we'd have to divide by 2, and that would be a little ugly. Here we'd have to divide by 3. Here we'd have to divide by -2. So using this nice clean y is going to help us stay a little bit nicer here. So this turns into y equals 5 minus 2x when we subtract the 2x from both sides. So we take that 5 minus 2x, that's what y equals, so we're going to plug it in for y. So 3x minus 2 times 5 minus 2x is supposed to equal 4. Notice, by the way, we substituted into the other equation. Never substitute back into itself. You'll always get a true statement and it won't tell you anything, so be careful about that. So we solved this equation for y, and then that y has to go into the other equation. So 3x minus 10 plus 4x equals 4. Collect some like terms here. 7x minus 10 equals 4. Add the 10, add the 10. Oh, that's nice. 7x equals 14, so x equals 2. Good. Of course, x equals 2 is not our solution. This is a system in terms of x and y, so we had better have a solution that is an xy pairing. So if that's our x, we got to plug that x back in to find our y. And we can plug it into any of these relationships. We can plug it in there, we can plug it in there. Heck, we can even plug it in there. This is already solved for y, so I think I'm going to plug it into that one. So, therefore, just keeping myself organized here, y equals 5 minus 2 times 2, so y had better be 5 minus 4, or 1. So our solution to the system is the point 2, 1. That's where both of the equations are true. That's where the lines intersect on the graph. That is the solution to our system. The other method you learned is elimination method, and 14 here asks you to use that method. And this is a nice candidate for the elimination method because there's no nice coefficient here. None of them are 1x or 1y. They all have, I'm not sure why my y's look different, sorry. So none of them have that nice coefficient. You're going to get fractions no matter what if ever you solve for x or y in either equation. Now that's not a bad thing. Having the fractions isn't a bad thing. But the elimination method, often called the addition method, allows us to kind of avoid dealing with those fractions for as long as possible. So it's a nice option when you don't have any 1 coefficients there. Now, just to make sure you know, the elimination method works based on our ability to add the same thing to both sides of an equation. Really, what we're doing is we're trying to add something to one side of the equation to get rid of the x's and y's without contaminating the other side. But if I added, say, 2y to this side, it would add a 2y to this side, and I'd just move my y's around. So the goal really is to add this to one side, and instead of adding this to one side and the other, I'm going to add the 4x plus 5y to one side and add its equivalent, 14, to the other side. That way I'm still adding the same thing to both sides. I'm just adding it in 2 different forms. But we really need to do that in a way such that one of the variables will go away. So the trick to make that happen, and you've done this, is to pick which one you want to get rid of. I'm going to get rid of the y's because they already have the negatives, and multiply by something that's going to make it so one of your variables is going to disappear. So what, 8x plus 10y equals 24. Why did I get 25 here? It's a 35. You got to watch me on those things. I'm working fast, so if I make little boo-boos like that, try to work around them or let me know, but I'll try to avoid them as much as possible. So we've just manipulated the forms of these. This is the same equations. They graph as the same lines. We've just changed their size a little bit so these 10s are additive opposites of each other. But now still, again, I'm going to add this to this side of the equation and get 23x and no y's. But legally, we're supposed to add the same thing to both sides. So I'd have to add this to the other side. But since this equals 24, I'm just going to add the 24 version of it instead and get a nice, what, 59. Is that 59? Yeah, I think it's 59. So x is going to equal to, what, 59 23rds. Well, gosh, 59 23rds is ugly, isn't it? I didn't happen to do anything wrong in there, did I? Oh, yeah, it's a 28. Why didn't somebody tell me that was a 28? I should hear your voices over the internet go, dude, it's a 28. So instead, what should that be? That should be 50, 63. Brain's not working. So 63 23rds, which really isn't any better when it comes to simplifying it, but 63 23rds. Let me just double check again. 15, 10, 35, 8, 10, 28, 23, 0, 13, 63. Yeah, okay. Hey, numbers ugly. Sometimes numbers are ugly. Never be afraid of ugly numbers. So that's the x. If we want the y, we're going to plug it back in. And again, we can plug it back into any relationship we know. We can plug it back into that one. Heck, we can plug it into those if you really wanted to. I'm going to plug it into, gosh, they're all ugly. I'm going to plug it into this one just for the fun of it. So 3 times 63 23rds minus 2y equals 7. 23rds are ugly there, but, you know, as I said, what are you going to do? 189 23rds. Gosh, I hope this is wrong. Minus 2y equals 7. I might multiply by 23 just to clean that up. 189 minus 46y equals 140, 50, 61. Minus 189 minus 189. So let me jump up here. Negative 46y equals negative, what is that, 28? 28. Y equals negative 28 over negative 46. And y equals, 14 23rds? Well, that one's a little bit nicer. If I happen to make some numerical boo-boo in there, you'll forgive me, I hope, based on the speed. But that's our elimination technique. It does tend to be nicer. Notice these fractions are ugly, but we avoided them through most of the problem. If we had tried to do this by substitution, we'd be stuck with those fractions immediately. So when the numbers are nasty, elimination method can be beneficial, but you still have some nasty numbers. The substitution method, if you are stuck with fractions, if this is a nasty number, you can have to work with fractions earlier and in a more difficult way often. The nice thing about substitution, though, is it works even if these aren't like terms. In your section where you're trying to find the intersection between like lines and parabolas and circles, for elimination method to work, you have to have nice like terms. For substitution to work, you have no such restriction. So substitution is a more general tool, but often the numbers are nastier. Elimination is more specific. You have to have the nice like terms, but it can be much nicer and much cleaner when the numbers are nicer. Okay. Speaking of larger systems, number 15, kind of a favorite question of mine. Given 2 points, you were able to make a line. Given 3 points, 1, 3, 3, negative 1, and 4, 0, given 3 points, they should make a parabola. Any 3 points you want are going to define a unique parabola. The nice thing about a parabola is we know what parabolas should look like. Parabolas should look like y equals ax squared plus bx plus c. If you're going to be a parabola, you have to have that structure where at least a is not 0. So if you're going to try to figure a parabola out, you need to have 3 numbers, a, b, and c. That's 3 variables. So if we're going to build a system with 3 variables and 3 unknowns. Now, of course, we have the x's and y's are in the way too, but the nice thing is we have a bunch of xy pairs. One xy pair for every equation that we need. For example, this xy pair here, the first one, 1, 3, says that you will get a y value of 3 if you let those x's be 1. 1 times a is a, 1 times b is b, and c is just c. So that's an equation. This point says you'll get a negative 1 if you let the x's be 3. 3 squared is 9 times a. 3 in for the x is just 3b plus c has to equal negative 1. And again, I'm just plugging in the 3. That has to equal negative 1. At 4, you'll get 0. So this is going to equal 0 when x is 4. 4 squared is 16a plus x is 4, so 4 times b plus c. So we have 3 equations with 3 unknowns. We're kind of used to the unknowns being x's and y's, so it can be a little counterintuitive that the x's and y's become our solid numbers and the constants a, b, and c become the variables that we're looking for. But still, it's 3 unknowns, 3 equations we can solve for a, b, and c. Now you have 2 methods. You have your matrix method, which is an okay method for checking, or if you're told, go ahead and use the matrix. But we also need to be able to solve these by hand. When we solve those by hand, we're essentially using the 3-variable version of the elimination method. So we do the same thing we did there. Pick a variable to eliminate. I'm going to call these equations 1, 2, and 3, just to be able to refer to them. Use Roman numerals to not confuse things. So if I want to get rid of variable C, we might take equation 1 and subtract equation 2. Or if you prefer, add the negative of equation 2. So that's a plus b plus c equals 3. I switched that order just because, I don't know, it seems prettier. And the negative of equation 2, so negative 9a minus 3b minus c equals 1. Make sure that negative gets multiplied by the 1 as well. And we get a nice negative 8a minus 2b equals 4. Or if you prefer, 8a plus 2b equals negative 4. If you like the negative over here instead of over there. It's up to you. It's your equation. And this is equation 4. Now we only have 2 variables. If we had 2 equations with 2 variables, we could solve. So we're going to use another pairing to make another equation. Important though, we used it with these 2, we got rid of the c. In the other pairing, we also must get rid of the c. So this is an equation in a and b. We need another equation in a and b. So we have to make sure we're a little careful about that. So, well, it doesn't matter which pairing we use. Let's use 1 and 3. So 1 and the negative of 3. Again, with these labelings, I'm just trying to keep myself organized. Staying organized is really the key to making this nice. But again, a plus b plus c equals 3, and negative 16a minus 4b minus c equals 0. I could probably save myself from some work if I made this negative and that positive, but eh. So negative 15a minus 3b equals 3. Let me make sure that's okay with that. Okay. Or again, 15a plus 3b equals negative 3 might be nicer. So that's equation 5. So 2 equations, 4 and 5, with 2 variables. So if we had 8a plus 2b equals negative 4 and 15a plus 3b equals negative 3, we should be able to solve those. That new system. And again, this is 4 and this is 5. Now, to solve that system by elimination, we need some of the variables to match. It's probably better for the b's to match here. So how about 3 times equation 4 and -2 times equation 5? That's going to give us an 8a plus 6b equals -12. -2 times that's going to be, what, -30a? That's ugly. Minus 6b equals -2 times that's going to be, what, +6? Yeah, cool. Those are going to go away. It's nice. So we could, what, -22a equals, what, -6? So a equals 6/22, so a equals 3/11. And again, 3/11 isn't the nicest thing we've ever had to deal with, but you want to find out what the b is. Well, that 3/11 would have to go back into a relationship between a and b. 4 and 5 are both relationships between a and b, so substitute a equals 3/11 into either one. I'd use 4 probably, into 4. And you have 8 times 3/11 plus 2b equals -4. And you'd solve that, you'd find b. Once you have b, you can sub a equals 3/11 and b equals whatever b equals into equations either 1, 2, or 3. I'd probably use equation 1. And then find c. Once you have a, b, and c, you know what your quadratic is. This back substitution part, again, I know you guys have done this, so I'm just kind of waving my hands at that a little bit, and it's on the PDF if you want. So again, the key here is 1, staying organized, and 2, making sure if you decide to get rid of c in your first pairing, you have to be consistent and get rid of c in your second pairing, because your goal is to build your 2 equations with the same 2 unknowns. And again, make sure to write your answer once you know a, b, and c. You know this would then be 3/11 x squared plus whatever your b is, x plus whatever your c is.